Hello, everybody. Welcome to the first session in the How to Build and Train Your AI Model program, which is sponsored by Houston Community College and my nonprofit, InspiredKid.org. So first, I'd like to start with a quick introduction to the entire program, starting with our course syllabus. So here we can find the entire course syllabus and everything that I'm planning to show, and specifically for session 1 today, we're going to be covering what is AI with a brief overview, as well as the different types and subtypes of AI. Then we're going to get into an introduction for Python and how it can be used in AI, and then we're going to dive into the math and all of the foundations of math that are needed for machine learning. So throughout this course, I'm going to be using several different reference books, and all of these books can be found online if you Google and search for them. So feel free to be able to find the books if you would like to for your own personal reference during the time between the lectures. So this first lecture is today on Friday, February 28th. However, the future sessions for week 2 are going to be on Saturday, March 8th from 9 to 12 p.m. when we're going to be covering recurrent neural networks, one of the types of deep learning that can be used for many different applications. Then in week 3, it's going to be on March 24th, a Monday, from 5:30 p.m. to 8:30 p.m., and we'll be covering convolutional neural networks, another type of deep learning used for image processing. Then in week 4, on March 31st, also another Monday, we are going to be from 5:30 to 8:30, walking through some of the labs that we're going to be using in previous sessions, so we can have a more interactive learning experience. So all of the labs that we're going to have allow you to have a more deeper understanding of the machine learning concepts and different ways of implementing them in Python. And all of the labs are going to be hosted on a platform called Google Colab, which allows for hosting of labs on a computer environment. As long as you have access to internet and a computer, you'll be able to run all of the labs in this course on a high-level GPU offered for free by Google. All of the labs for this course can be found on the InspiredKid.org GitHub. So currently we have some labs from the MIT Introduction to Deep Learning course, a Python tutorial that we're also going to be going through today from the Stanford CS 224N course, as well as many different files of code that are associated with one of the books I'm going to be using as reference for this course. So I think we should also introduce that we have a Discord available for this course. So that way, if you have any questions, you can have them answered by me, the other instructors, or even your own classmates. So it'll be a very open and discussion platform where you can be free to ask any questions you may have outside of the lectures. So now let's get straight into what are the different types of AI, as well as what is AI in general, with the Deep Learning with Python 2nd edition book by Francois Chollet. Francois Chollet is actually one of the founders of a crucial machine learning platform called Keras, and he wrote this book to help introduce different types of AI. So first, I'd like to show a diagram that shows the relationship between artificial intelligence, machine learning, and deep learning. So artificial intelligence is the full class containing machine learning, which is more simply a way to make machines learn. And then inside of machine learning, there is the concept of deep learning, which we will be now covering. So first, in artificial intelligence, it started in the 1950s when several different people from the Dartmouth College came together over the course of a summer because they wanted to create a machine that could mimic all different aspects of human intelligence. Although they were unable to succeed, this started the revolution of AI and prompted many other investigations into all of the topics. Then in machine learning, there was two main people called Lady Ada Lovelace and Charles Babbage, who invented the analytical engine, which was the first of its kind computer that could process many different computations at a mathematical level. It was quite visionary. However, Lady Lovelace commented in 1843 that perhaps would a machine ever be able to create its own unique content because humans are providing everything it knows? This question was prompted to have many further research, and eventually in Alan Turing's 1950 paper, he introduced the Turing test as well as other concepts that would be extremely important for artificial intelligence. So, in this paper, Alan Turing also introduced the concept of machine learning. So in classical programming, you usually take different rules and data to be translated into outputs. However, in machine learning, this was revolutionized by instead having data and outputs and turned into rules. This was extremely critical because previously in tasks, the rules would have to be created by hand to classify different parts of data, which was extremely complicated, and anytime something was encountered that did not match the set of rules, it would be extremely difficult to adapt your rules in order to account for the new data type. However, with machine learning, these rules could be created by the algorithm for easier classification at a much more efficient level. So, machine learning has the subtype of deep learning, and overall, machine learning needs three key concepts in order to work. First, input data points. So for example, if we want to have a speech recognition task, these data points would be different files containing the sound of people speaking. Second, the examples of the expected output based on these inputs. So in the speech recognition, it would be the different transcripts of those sound files generated by humans. And finally, we need a way to measure if our algorithm is doing a good job. So in our speech recognition case, this would most likely be through a measure of the percentage of different images that are being the different speech files that are being correctly recognized. So let's take a more concrete example with some different data points on an X and Y plane. We have white and black points. So the inputs to our machine learning algorithm would be the different coordinates of these points on the XY plane. The expected outputs would be the colors of our points, either white or black. And in order to measure how well our algorithm is doing, we could have the percentage of the points that are being correctly classified by our algorithm. So if we want to separate the white from black points to make this classification task easier, we could use a change in the coordinates by first taking our raw data, moving and rotating the X and Y axes to split the black and white points. So that is represented so that to the left of the y-axis, where x is less than 0, all the white points are shown, whereas to the right of the y-axis, where x is greater than 0, all of the black points are shown. This representation seemed to be very easily done, and perhaps makes you wonder why you would need a classification algorithm in order to do this. However, if you think about more complex tasks, such as classifying handwritten numbers, it would be much more difficult to change the more brittle rules of classifying the difference between a 6, an 8, a 1, and a 7, and all the other handwriting styles and numbers that there are. So machine learning is truly revolutionary in this aspect, as instead of having humans perform all of these manipulations of the data, we could use machine learning algorithms to find all of the best manipulations that make these classification tasks easier. So I'd actually now like to introduce that we are going to be doing a classification task for handwritten digits using a type of machine learning called convolutional neural networks, which is extremely crucial for image recognition and classification. Now I'd like to cover why deep learning is deep, and this deep is actually not a reference to any deeper understanding achieved by these methods of deep learning, and rather it is actually a reference to the many different transformations of the data that are learned. So as we saw in our coordinate point example, the way that we rotated and moved the x and y axis was an example of a transformation of the data. And in deep learning, many different transformations are used to make classification tasks easier. This is done through models called neural networks. And although with the word of neuron, it sounds like it may be referencing to architectures used in the brain, neural networks were actually inspired by parts of the brain, but they are not based anything on the human intelligence or brain. And many parts of the brain do not work at all like neural networks. So, to introduce neural networks in a more concrete form, let's take the example of handwritten digit classification. Let's say we have the digit 4, and we will take it through many different layers of classification and transformations in order to achieve a final output that this digit is indeed a 4. If we expand this further, we can see that between each layer, we look at different representations of the data. So first, we look at the high-level features, including the entire 4. Then in the second layer, we look at representations in a more detailed layer in a mid-level kind of features with more specific parts of our 4. And finally, in layer 3, we look at the specific pixels in our digit 4 and their different colors of the pixels in order to output the classification of 4. So at a more in-deep level, deep learning first takes an input of X, uses different layers transforming our data input and outputting predictions. I would also like to introduce the term called weights, which determines how these data transformations adjust the data that we input. And the goal of this neural network is to find the right weights and values for those weights that allow the data transformations and representations to be done in the best way possible to achieve the highest accuracy. This is done usually by comparing the predictions to the actual targets that are achieved and also inputted with our X as outputs. Then we compute the difference between these predictions and the actual outputs that should be seen to find a value called loss, which is extremely important in later machine learning applications. Then we use this loss value and use a second machine learning technique called an optimizer to change the weights in an extremely slight manner so that way they get closer to the values that will achieve the best accuracy later in the neural network. So in summary, this neural network works by first taking an input of X, putting it through several different transformations based on weights that are optimized through the neural network. This allows us to have predictions of classification tasks, which are then compared to the actual outputs and then computed to have a loss value, which is then used back at the beginning of the neural network in a recurring loop to optimize the weights to have the highest accuracy of classification in the machine learning model. So deep learning seems to be a very important technology. In fact, it has actually achieved many different accomplishments so far. These includes extremely accurate image classification, which we will actually be doing later in several different labs with our convolutional neural network architectures, handwriting transcription, which we will be doing in one of those labs to classify handwritten digits from 1 up till 9 and 0, different digital assistants such as Google Assistant or Amazon Alexa, which I'm sure that many of you watching actually have, including Siri on your phone, which are actually powered by a type of artificial intelligence called large language models, which we will be covering in the second part of this course. There have also been many other achievements in artificial intelligence, including self-driving cars, which work on the same aspect as image classification, but instead use images of maps and roads in order to make the decisions of turning left, right, stopping, or other examples of movements like that. So machine learning and deep learning may seem to be extremely powerful. However, there is a lot of short-term hype. Even beginning in the 1960s, we had many promises that were not fulfilled in a couple of years. Just like in the movie Back to the Future, we were promised flying cars by 2015. In 1967, a pioneer named Marvin Minsky said that within 3 to 8 years, they would be able to create a machine that had the general intelligence of an artificial human being. However, now in 2025, this achievement is still long in the future, and because of this failure to fulfill this promise as well as many others, funds and research investigations into AI dried up, starting the first AI winter, which is called a winter because it was reference to the Cold War, which was currently happening at the time. Then the second AI winter occurred in 1980 when a new take on AI called expert systems was having several different initial successes. However, later it was found that these models were extremely expensive to maintain as well as very difficult to scale, leading to the second AI winter with little investment and little innovations. Now, deep learning and AI as a whole may have had some failures in the past. However, there are extremely important long-term expectations. In the future, AI may even become your best friend, your personal assistant, and may help to even save lives. In fact, as an example, in my scientific research that I'm doing concurrently to this AI course, I'm actually going to create a type of AI that will help use genetic sequences to help cure over 10,000 genetic diseases. And the future of AI as a whole looks just as bright as that and even beyond. So now I'd like to take a step back and look at the previous types of technology before deep learning, as sometimes deep learning may seem like the best approach to every problem you may encounter, but there were some previous methods that could possibly be better. First, the earliest form is called probabilistic modeling, which uses actual mathematics and statistics to classify tasks. In fact, methods such as the naive Bayes algorithm and the logistic regression algorithms were implemented by hand far before computers were invented. The naive Bayes algorithm works by having the assumption that all data points inputted to it are completely independent of each other, which is why it is a naive assumption. And the logistic regression method is considered to be similar to naive Bayes, and however both of these may seem early and useless, they are actually extremely useful for simple and versatile tasks. Before deep learning, there were also different forms of early neural networks. In fact, in the 1980s, the first successful application of a neural network was implemented in the United States Postal Service, where a neural network called RNNs was used to read zip codes on different envelopes to speed up the processing of packages to be sent quicker to their locations. A different method before neural networks called kernel methods eventually made neural networks go away for quite a time, and because of this, they were so revolutionary, and more specifically, the support vector machine was extremely revolutionary as well. And this works by finding a nonlinear boundary between different data points that are inputted in order to perform the classification task. This is done by first having the data put onto a coordinate plane or a high-dimensional representation, depending on how many dimensions are in each data point. Then a plane or line was found between the many different data points that separates them into two different classes. This was extremely useful as it seems to be very helpful in classifying things quickly. However, it eventually became proved that they were extremely hard to scale due to their simple logic, and they were also not good for complex tasks like image classification because they could only separate two boundaries and could not understand complex representations such as images. Then decision trees, which are similar to flowcharts, were now implemented as the most common in the 2000s, which replaced the kernel methods. And as you can see in this diagram, it first takes input data and asks several questions about the data in order to categorize each data point into its own separate categories. So the main algorithm that is used for this is called the random forest algorithm, which is implemented by having many different decision trees and then having a random algorithm go through them, eventually fixing that randomization to be at a more accurate level to classify many different tasks. Then in 2014, a method called gradient boosting machines, which are similar to random forests, took over because although unlike decision trees, it actually has a method called gradient boosting, which specifically addresses the weak points that a machine learning model may have, making it one of the most impressive and best algorithms of its time. Then, in the early 2000s, neural networks reappeared because of their extreme versatility. For example, in the ImageNet Large-Scale Visual Recognition Challenge, an extremely popular machine learning competition in the early 2010s, there was an entry that used neural networks to achieve an extremely high accuracy of 74.3% in the challenge. And although this may not seem like a high percentage today, it was extremely crucial in later advancements. In the next couple of years, it eventually reached 96.4% accuracy, an extremely high level for its time. Since then, many different neural networks have been used in practice in order to perform many different tasks and accomplish and solve their problems. So deep learning may just seem like another method that is out there. However, what makes it so different is the solving of the issue required from the previous requirement to define different rules in a classical programming problem. So this is called feature engineering, where you would manually go and solve a problem by defining different rules in programming to classify different items. However, this was shown to be extremely difficult because if you have a new data point that does not conform to these rules, all of the rules would be ruined, and you would have to create new rules that take into account all the previous rules, and also create new rules to classify new data points, and it was all too confusing. So machine learning has its own feature engineering methods that allow it to create these rules and classifications at an extremely high accuracy rate. So today, there are many different machine learning algorithms that are available, as well as many different packages available to make these machine learning completion tasks as easy as putting together Lego bricks. So to see which technologies were most common, we can look at a survey done by Kaggle, which is a dataset providing company that provides many different datasets as well as challenges for users to complete to win many large cash prizes. And they surveyed the top 5 of every competition they had since 2017 for which software they had used in their competition. And most commonly, you can see that deep learning methods and classical methods were used. So 40 competitions had the library called Keras used, which is an extremely common library that is now built into the larger library called TensorFlow, which is used most commonly in machine learning to build convolutional neural networks, as well as other types, and the light GBM and XGBoost libraries for classical programming, such as the decision tree methods that I detailed previously, which are used for other tasks as well. In a wider survey of all of the competitors that they found on Kaggle's website, the package called Scikit-Learn was 82.8% used in the machine learning field. Next was TensorFlow and Keras, which, as I said, have been combined since the survey was performed, as well as XGBoost, PyTorch, and LightGBM, showing a trend between the top users of different workflows as well as all of the users. And all of these libraries are extremely critical as they make machine learning code and programming extremely simple. So now you may be wondering, if there were all of these technologies that existed before, why should I be doing deep learning and why should I be doing it now? However, I would like to counter that there are many different factors that are increasing deep learning's popularity, such as hardware, more available datasets, and advances in algorithms. In hardware, between the year of 1990 and 2010, CPUs available to consumers are now faster by 5,000 times. And companies such as NVIDIA have been creating GPUs called graphical processing units to make photorealistic video games. And more recently, they have been repurposed for the AI and machine learning scope, as they can have many different parallel computations, which allow training for convolutional neural networks and other types of neural networks in deep learning to be extremely easier and faster. In fact, today, a GPU called the Titan RTX that costs $2,500 now can deliver the amount of computing power as 500 times the most powerful supercomputer from 1990. In fact, more recently, in 2016, a new type of computing chip called tensor processing units, developed by Google, can be used for much faster parallel processing as they are now designed for specific machine learning tasks. In fact, when these tensor processing units are assembled into configuration called pods, as they are built to be at a scale of 1024, they have 10% of the entire computing power of the most current largest supercomputer, which has 27,000 GPUs. That means that 1,024 TPUs, tensor processing units, are equivalent to 2,700 NVIDIA GPUs. In datasets, although AI may seem to be the main forecomer that is making all of the new advancements, it is really powered in the backend by data. And without data, none of these advancements would be possible. So, for example, throughout the internet and its rise in the coming and past years, there have been many different user-generated available datasets, such as Wikipedia for language and YouTube videos for image and video content. There is so much content available now, open source, that it can be used to train these AI models and make them at an extremely high accuracy for many different data points. In algorithms, since the late 2000s, there have been many different increases in neural network and other technologies in deep learning advancements, including ways for training as well as the optimizers for the weights, which I detailed previously. Besides the top three main advancements, there have also been many new investments into AI. In fact, in a graph of the total investments for AI startups, in 2011, there were less than $1 billion being put in, but in 2017, there were over $16 billion. In fact, more recently in 2024, the estimate is about $150 billion for these AI startups, showing the exponential trend of AI and its interests. Additionally, deep learning packages have been democratized, so now anybody with expertise in the coding language of Python can create machine learning models for their very own tasks extremely easily. Now, since I've told you about all of these previous technologies that have existed before and they quickly fade away within a decade or so, you may be thinking if deep learning will be the same. However, there are many different aspects of deep learning that show it is here to stay for the AI revolution. First, simplicity, because deep learning removes the need for those handwritten and hand-created features for classification. Second, scalability, as deep learning is extremely available to be implemented on GPUs, which can allow it to take full advantage of the exponential scale of other technologies. Third, its versatility and reusability is unlike previous machine learning approaches, as some neural networks can actually be trained on additional data without restarting from scratch, allowing them to be extremely useful for large-scale implementations.